All right, so we're going to be talking about more on these Yukawa interactions. Let's take a look at what these Yukawa interactions look like. And then based off of what we talked about yesterday with the Dirac, with the Dirac Green's function and the Klein-Gordon Green's function, we'll be able to sort of take a look at how these work within the context of Yukawa interactions. So we'll start off just by looking at what a Yukawa interaction is. So we want to write our Lagrangian now. We've talked about Lagrangians for scalar fields. We've talked about Lagrangians for spinor fields. Let's couple these two Lagrangians together now. So what we have is a Lagrangian for a scalar and a spinor. And then we're going to have this interaction term. This is going to be the Yukawa interaction term. So I'll just put interaction. And what this looks like is the scalar Lagrangian. So this is going to be 1/2 d phi squared. It's the same thing as d mu d mu. Then we're going to do minus m squared over 2. And this is going to be the mass of, we have to start being a little bit more specific. This is going to be the mass of the scalar field squared over 2 times the scalar field itself squared. And then we're going to have our Dirac term, so plus let's see here, I bar gamma d mu, right, minus m, the mass of our spinor field squared times complex conjugate times the spinor. And then we're going to add this Yukawa term, G complex, real, and phi. So we have the spinor part. We have the spinor part, or that's the scalar part, sorry, the scalar part, the spinor part, and the interaction part. And the reason this is the interaction part is because we have spinors. These things are spinors here, and then we have our scalar. And our scalar is coupled to our spinors. The strength of the coupling between the two is given by this G factor. Okay. And so what we can have, we can break this up also. We can have just a scalar field with, or just a scalar Lagrangian with just the interaction term, or we can have just a spinor Lagrangian with in the presence of interactions, right? So, but this is the whole thing, right? So we theoretically could have a Lagrangian without the Dirac term in it, and just the scalar and the interaction, or vice versa. We can have it just with the Dirac term and the Lagrangian and the interaction, and no scalar part. But when we have both, we're being complete here, and the book goes over what these look like. We're gonna detour a little bit now and talk about these potentials or not potentials, but we're going to add potential terms to this now. But we're going to do this sort of one bit by bit. So I'm going to start off, I'm actually going to work on the Dirac Lagrangian and work on its potential. Because if I remember correctly, we worked on the potential already for the this scalar. Scalar and spinor, they start with an S, and for some reason I want to say scalar when I mean spinor and spinor when I mean scalar. Got a little bit of dyslexia or something going on here, I guess. But anyways, if we recall from the last video on self interactions, we had this I'm just sort of going over a recap here. We had this general function. It was a function of space and time, and it was an integral over all space of the potential dv at some point y mu with respect to phi dv. The potential again is a function of was the function of the spinor value, and the spinor value was a function of a space-time coordinate. So that's what that is, and that's the height. We said that was approximately the height of a delta function, and then we had these special functions that sort of acted as the delta functions themselves, or the waves that constituted the delta functions. And this is what we had last time for our self-interactions. We're going to have something similar for our spinor field. So let's take a look at what the potential looks like for a spinor field. So if we remember, our spinor Lagrangian, or our Dirac Lagrangian, looked like this. Plus v, we're going to add this potential term here. It's a function of the spinor and its complex conjugate. So we can figure out what the potential is for this by writing out our Euler-Lagrange equations. So here's our Euler-Lagrange equations. And what we're going to do, what we're going to be able to see is that we're going to be able to isolate the potential, right? Because, so the derivative of this with respect to this was just going to be all of this right here, because it's sort of like a constant, right? When we're taking a derivative. So we're going to have I gamma mu d mu minus m. Okay, and then we're going to have the rest, right? So when we take a derivative with respect to the derivative, right? So that's going to be, well, this term here. So this term here is actually going to contain derivatives of this. So, well, actually, no, I take that back. When we distribute this, we're gonna have a derivative on this function right here, right? We're not gonna have a derivative of this. What we see here actually is there's actually no derivatives of the complex value of the spinor, or the complex conjugate of the spinor, right? So this term actually is going to go to 0, right? And what we get is just this term right here, okay? And so this is going to be v like this, and we want to take a derivative of that. So let me just move this. Okay, and then we can move one to one side and so forth. But what we end up getting is that we have this now, right? So what we can do is we can say, just like we did for our spinor field or for our scalar field, we can construct the same thing for our spinor field, right? So we have this for our scalar field or Klein-Gordon field. We can do the exact same thing now with the spinor field because now we have an expression for this, right? It's just going to be this. But now that we have this, we'll just put this in to our integral that we're going to construct. All right, so we're going to have a sum over all space, and then what I'll do is I'll just copy paste this guy in here, copy paste, like this. And what we actually need to do, just to be a little bit more complete, is we need to say that this is a function of y mu, and this is a function of y mu. And then we have our special functions. Okay, and this is our general function. And we talked about this in earlier discussions, but just as a recap, we can compare this with this guy up here, and there's really not that much of a difference other than the fact that these are spinors, right, and these are scalars. And what we can do now is we could say, well, if these are spinors, then that means this here has components to it, right? Because this is a direct spinor. It's a 4-component object. This, therefore, has to have components to it also. But it needs components. This special function has components that sort of dictate the interactions between a spike at y mu, right, at y mu. So we're going to have a spike at y mu, and we're going to have a spike at x mu, right? We label them different coordinates, what I just did with the beta. So that means we have to do the same thing here, because again, the Green's function is the thing that describes the interaction between all the components. So this thing is a matrix, right? And visually, we can look at it like this. I really like this visualization that I came across while I was reading this book. The book doesn't really have the visualization per se, but what you can do is you can say, well, we have this field, and right here and right here we have these delta functions, right? We have these delta functions, And these are described by spinors, right? So this is a spinor alpha. This is a spinor beta. We're just labeling components. This spinor here looks like 0, 1, 2, 3. The spinor here is a vector, or not a vector, it's a spinor, but it's got components to it. We say it's a spinor again because of the way it transforms. That discussion goes a long way back from like chapter 3, I think. And we need an object that tells us how this interacts with this term, how this interacts with this term, this interacts with this term, and this one interacts with this term. Then we need to go to the next one. We need to understand how this interacts with this term, how this one interacts with this term. And what you see is that we are essentially constructing a matrix, and then we can do the same thing for our gamma, or these interactions, right? So all of these interactions are existing between all of the components, okay? And so what this means is that we're constructing a matrix. And I think we looked at this a little bit earlier, but our special function looks like this. Uh, 1, 0, 2, 0, 3, 0, and so forth. Where, say, this is the interaction, this 3, 0 interaction, is the interaction between this here and this one right here. And we're doing that for all of the interactions. Remember, and so this 3, 0 here is the interaction between this here and this here, right? So those might be different, they might not be different, which is why we can't really say anything right now about the symmetry of this matrix. And so, to be a little bit more complete, we found out what our potential is. Potential, again, looks like this. And so our special functions are going to give us something that looks similar because, again, these special functions talk about potentials. The potentials are the spikes in the field. And what we have now for the dynamic equation that describes the movement of these potential functions, again, looks like this alpha, or actually, alpha sigma and sigma beta, x mu, y mu, and we have a delta function, x mu, y mu, alpha beta. Right, so we've talked about these special functions now, and again, I think my videos are going to be a little bit shorter than what they initially were. My initial videos were going about 30 minutes. I think I might make these a little bit shorter. I found that even myself, it gets boring when you see that timestamp on the video that says an hour. right? So I found that I think for most people, anything between 15 and 25 minutes, I think is probably good. And so with that being said, I'll just talk about what we're going to do in the next video. The next video is going to talk about, we're really just going to take these functions, or these Green's functions for the Dirac equation, and we're just going to prove. We're going to prove that they work by putting them into here. Right? We just want to see that these things work. Given that we have a potential that looks like a delta function, we're going to put this proposition of a delta or a Green's function. I actually didn't write it down again, but I wrote it down in a previous video, and we're just gonna really prove that it works, okay? And then after that, we're gonna talk a little bit more about Yukawa interactions for. We're just going to continue talking about a little bit more about Yukawa interactions, and then we'll jump into gauge interactions, and those will be interesting and fun. And then we're going to get into quantum mechanics. So keep in mind that up until this point, we're still talking classical fields. We haven't really touched quantum at all yet. Quantum's going to come into play when we start considering the commutation relationships between these fields. What we're going to find is that these fields are again, they're dictated by a Lagrangian. The Lagrangian's a function of the position and the momenta, or the time derivative of the positions or the values. What we're going to want to do is we're going to find that there's these things called there's this thing called a canonical momentum associated with these fields. So in essence, we can be able to convert these fields between two things that are going to be very useful to us. Then we're going to take those two things, commute them together, and find out that there are some interesting properties that arise out of these fields when we do these commutation rules. And these properties are going to help us see that there are these creation and annihilation operators that work with each other to annihilate particles. And those are going to be the things that are unique to these fields, because fundamentally those creation and annihilation operators are the things that manifest themselves in the real world as excited particles or de-excited particles. Okay. And then we'll quickly get into propagators after that. And that's all going to be in chapter 8. But I hope you guys enjoy this kind of stuff. If you do, please hit that subscribe button, and I'll see you guys in the next one. Bye.